So, you're welcome once again to our series of classes on VPH 527. I hope you can hear me loud and clear. So today we are just going to take it up. We'll continue from where we left off in the last class. We'll continue from where we left off. I could see excuse on phone being dead, but I think you can connect in a cluster. Even if someone's phone is dead, it doesn't mean you cannot walk up to the next person. You can congregate in clusters so that you can participate in the class. Yeah, I know you're not living together, but for the purpose of this class, someone can decide to visit a friend or stay with another person. I'm just saying, staying away from the class is not the way to go, because that excuse will not, it won't suffice. Some of you used to visit your friends. You go to another street to watch football. I think maybe this is the time to activate such a commitment. So without wasting time, I'm just going to take it all from where we left off in the last class. Now, during that last class, I concluded with binomial distribution. I told you that generally in statistics, we have different types, two categories of probability distribution. Okay? We have discussed the philosophy of probability that statistics is actually based on. And that is, of course, the empirical philosophy, okay, which is largely objective. It is based on experimentation. And of course, I told you probability distribution generally could be categorized into two. We have the discrete probability distribution. We have the continuous probability distribution. The discrete, again, we deal with integers. The discrete, again, we deal with just integers. Okay? While in continuous, your random variable s can take a value between two whole numbers. That is what we mean by continuous. Now, I gave you the different examples under the discrete probability distribution. We talked about the geometric, hypergeometric. We also talked about binomial and Poisson. Myself, for the purpose of this particular course, we're going to limit ourselves to both to binomial and Poisson distribution. Before the end of that last class, we took off on binomial distribution. I elaborated on the different properties of binomial distribution. Of course, we have talked about distribution. What does distribution mean? Probability distribution. These are the probability of an event taking place. When you have it plotted on the table, or you have it on the table, then you call it probability distribution. Okay? And for the binomial distribution, we said usually binomial distribution is described as a binary trial. The repeat of a binary trial. A binary trial is a trial with two possible outcomes. Yes or no. True or false. In or out. Okay? that is a binary trial. So when you have a binary trial repeated n times, that becomes a binomial distribution. And we are also elaborated on the different properties of binomial distribution. That binomial distribution we talk of success, we talk of failure. The probability of success, the probability of failure. And I said they are both complements of each other. Okay? If the probability of success is 1/4, then the probability of failure is 3/4. So everything must add up to 1 because they are complement of one another. Now, the first example we looked at is that of the albino rat used for study hormonal regulation of a metabolic pathway. And I told you that usually in probability distribution, the success event is usually, it don't usually enjoy the first mention. Okay? Like the example you are seeing on your screen that talks about rats dying. You say dying is the event of interest here. Okay? So when you say 4 out of 20 rats died, it simply means the success rate we are looking at here is 4/20, which is the probability of success. It means the probability of failure will definitely be the complement of it, which will now be 16/20. 4/20 is 1/5. 16/20 is 4/5. Now, it's important you understand that before you begin to solve questions on binomial distribution, you must establish the probability of success and probability of failure, which I just did. And then you now apply these values to solve for any question that could be presented before you. Like on the screen, you have if 10 animals are treated with the drug, what is the probability that at least 8 will die at the end of the experiment? Okay? And again, I told you that the binomial distribution has a formula. Okay? It is n combination R, p to the power of x, our random variable, and q to the power of n minus r. That is the formula. That's the mathematical expression for binomial distribution. And I told you that this formula, you should be abreast with it from time to time because you are going to be applying it, okay? And I told you for every question I give to you, you must first of all state the formula. Number one, you want to tell me the distribution you are dealing with. For instance, I can give you a question and I may not deliberately tell you, I may not give you a hint of what type of distribution. We have a different type of distribution. We have binomial distribution, Poisson distribution, as we're going to soon discuss. We have normal distribution. We have different kinds of distributions. Okay? And I've told you, how do you recognize a binomial distribution? How do you recognize a Poisson distribution? How do you differentiate distributions? It's important you get to understand all this. So, the first question here is you want to recall the concept of inequality. When you say, looking at the screen now, I'm going to activate my laser pointer. Looking at the screen, if 10 animals are treated with the drug, what is the problem? That at least, it's important you are familiar with inequality sign. So we say at least 8. That at least simply means out of 10, at least. It means it could be 8, it could be 9, it could be 10. At least 8 will die. Now, it's important you take note of that statement. I mean, that phrase rather that follows it. This particular phrase that follows it would die. Okay? It simply means that the question is in phase with our distribution our distribution pattern, okay? Because the distribution focus is on death. Then the question is now if faced with it, okay? So in that case, you begin to solve by saying, okay, the probability of x greater than 8 is our interest, okay? Again, I wrote that in the other class. Maybe I should also put it down here. So our interest here is the probability of x. You call that x is our random variable, s greater than 8. Because the question says, what is the that at least 8? At least 8 means it could be 8, it could be 9, it could be 10. And again, I told you, of course, in inequality, the right way to actually articulate this should have been probability of x greater than or equal to 8. But that equality something is usually not added when you have your line graph divided into 2 in statistics. So we put it this way, but it also implies that. So it simply means you are finding the probability of x is equals to 8, x is equals to 9, and x is equals to 10. It is the summation of this individual probability that will give you the probability of x is greater than 8. So it will be probability of x equal to 8 plus the probability of x equal to 9 plus the probability of x equal to 10. So it is the sum of this probability that will give you the probability of x greater than 8. I hope that is clear. Am I still with my class? Are you still there?
Yes, sir.
Okay, great.
Yes, sir, we can hear you.
Okay, great. So that is how to calculate this. But please take note of the statement I've just made. It is this straightforward because our question is in phase with our distribution information. Okay? Now, what happens in a situation whereby instead of saying would die in this statement, let's assume the question is rephrased, okay, to read will be alive. So the implication is that that question is not in the same phase with our distribution focus. Now, that carries a lot of implication because the focus of the distribution is that 20 rats die, okay? But when you say will be alive, now what you do in that situation, when your question is not in phase with your distribution, you are going to flip that particular question. How do you flip it? Okay, please listen carefully. So when you say at least, let me activate a whiteboard. Let me just stop this right there. And then activate a whiteboard so that I can illustrate what I'm trying to say here. Okay, so we have, if we say probability, the first instance we said at least 8 will die, that is P probability of x greater than 8. Okay, that's at least 8 will die. Look at it here. At least 8 would die. Okay, that's what we have in that question. But I'm not saying that what if the question reads, at least 8 will be alive. How should this be stated? At least 8 will. Somebody say you can't see the whiteboard. Can you all see the whiteboard? Can you all see the whiteboard?
Yes, we can see it.
Okay.
I can see it. I can see it. I personally.
Okay, good. At least 8 will be alive. Can somebody help me flip this to read to be in the same phase with the distribution? How do you flip this? Now, at least 8 will be alive. If you are to flip it, it simply means that at most 2 will be dead. Did you get what I just said? You call it at least 2 will be dead. That is the flip of this particular statement, so that it can be in the same phase with our distribution focus, the event of interest. Okay, at least 2 will be dead. That's what it means. Okay, at least 2 will be dead. Now, at least 2 will be dead. How would you express the probability of at least 2 will be dead? So you say this is equal to at least 2 will be dead. Okay? At least 2 will be dead, or at least 2 will die, whichever way you want to put it. Okay?
Sir, is it at least or at most?
What's the difference between the two?
At least means more than 2. At least 2 will die.
Okay, yeah, you are correct. You are correct, sorry. I think that's what I was trying to figure out in that statement. Okay, so the right statement should be at most, sorry. Let me get a pen and rub that off. Yeah, I'm glad somebody is following what we do. Let me see if a pen can rub that off. Okay. Okay. Now, the most important thing here is to know how to express this in inequality. At most, 2 would die. Thank you. That's the right way to state it. So at most 2 will die simply means probability of x less than or equal to 2. Did you get that? Probability of x less than or equal to 2. Because I said you don't need to add inequality like this to it. Okay? Do you all get the point? Hello? If you are listening, please indicate if you got this point. This is where it gets tricky. Okay, good. Chiamaka is with me here. Good. So this is how to state the inequality now. It's important you get how to state this inequality because this will now guide you on how to do your calculation. So when you now say probability of x less than or equal to 2, it simply means the probability of interest now will be P, that is probability of x less than 2 will now be the sum of the probability of zero, that is x equal to 0, now you have to start from 0, okay? 0 must be included if you are going down the line. Let me just draw, what do you call number line, okay? For number line, you're going to have 0, you have 1, you have 2, you have 3, you have 4, you have 5, okay? So you include 0 in your calculation of probability. So probability of x equal to 0 plus probability of x equal to 1, okay? Plus the probability of x equal to 2. So this will now be your answer. This is how to compute for your answer. But it's important you get this at this point. Is it clear to this level? Let's pick up now. Is it clear to this level?
Yes, sir. Yes, sir.
Oh, great, great, great. So how do you begin to compute for probability of x equal to this? Recall that the binomial formula is stated as what? N. Let me look for a pen, an eraser to bring this up. Okay. Okay, so the formula for your binomial is n factorial n minus x, bracket open and close factorial, okay, x factorial. Then you are now going to have your p, okay, to the power of what? Your x. And then you have q n minus x to the power of n minus x. So this is your formula, okay? So what it simply means is that you are now going to substitute. Recall that our n, what is our n from the question? Our n is given as what? As 10. Please don't forget that. So if you put 10 here for... This is the formula. Somebody is asking for the formula. This is the formula here. This is the formula here. It is usually stated as n combination x. N combination x e to the power of x. What do you want? So it's usually stated as n combination x. Okay? E to the power of x. So is this clear? The person asking for the formula, is this clear? Is this clear? Is it clear? Chiamaka, please respond if it is clear. So what you now do, which is the next thing to do here, is
Yes, sir.
okay,
You
great.
you said n combination x, p to the power of x, then q to the power of n minus x.
Minus x. Good, thank you. So now let's attempt solving for the first one. Let's attempt solving for the first one, which is probability of x is equal to 0. It's important I solve this so that you understand how it is done. So our n factorial, okay, n minus x factorial, x factorial, p to the power of x, q to the power of n minus x, okay? Now, our n is 10 factorial, right? Good. So you have 10 minus 0 in the case of x is equals to 0 factorial, right? And then you have 0 factorial. Can somebody tell me what is 0 factorial?
1.
Okay, good. 0 factorial is 1. Please, if you don't know that, please know it now. And you can see P. What is our P now? What's our P? What should be our P from that question? What should be our P? I'm not going to be writing P again. So I'll just put 1/5, right? To the power of 0. And what should be our Q? Okay? Our Q should be 4/5 from that question. And our n remains 10 minus what? 0. Okay? So n factorial, if you check up here, you see n factorial over 10 minus 0 factorial. So from this actually seems to cancel out. Okay? This seems to cancel out completely. While 1/5 to the power of 0 is equals to 1 in mathematics. Anything raised to the power of 0 in mathematics is what? Is 1. So, and that's resolved these two, okay? Now, what you are now left with is the one we have 0.8 to the power of 10. So it means the answer for probability of x is equal to 0 is 0.8 to the power of 10. I hope that is clear. Is it clear? Please take a moment to look at it.
Sir, good evening, sir.
Yeah, good evening.
Yes, sir, please, it's Ivan.
Ivan,
I'm really
good.
sorry, sir. I was not really able to log in very early.
Good.
So I don't really understand how we are solving for probability of x equals to 0, 1, and then 2.
We want to take us back to Egypt.
I'm really sorry, sir.
Just follow me from where I am at the moment. When you see the video, you'll be able to follow better. Otherwise, we are going to be stopping and then we are going to be going back. Another person will join in the next 2-3 minutes and want us to start on the again. So,
okay, sir, please.
yeah.
Okay, sir, please. Is it the first question or the second question we are solving right now?
It's still the first question. I'm just giving, I only made a modification to that question just to explain a different scenario.
Okay, sir.
Do you know how to solve the question? Do you know how to solve? Were you part of the class when we solved the first question?
Yes,
Yes,
sir.
sir.
We were part of the last class and we solved our hours and uploaded it to the classroom, sir.
Okay.
So
If
now,
you are
which
the first,
scenario now are
okay.
we considering?
Yes, I told you before we closed that last class that let's assume that I modify that question to read would be alive. Would be alive.
Life not die.
Yes. So that's what we are solving.
Yes. Okay, that's 2, 1, 2. Okay, sir.
Okay, sir.
Thank you, sir.
Thank you, sir.
You're welcome. So I hope that is clear with everyone. I hope that's fine. Can we move on?
Yes, sir.
Okay, good. So without wasting too much time, Then you can go ahead and solve for a random variable is equals to 1 and is equals to 2. And then you add everything together. The summation of everything will give you the probability of interest, which is at most 2. Which is at most 2. Okay? Any other question on that? All right, so I'll just stop this and continue sharing my slide now. I'll go back to my slide. Okay. Okay, so this way I stopped. So the same way, you can also solve for this second question. Okay. Now look at the second question. The second question reads that for parents, 2 parents rather, each 2 parents, I think it should be each has the gene. Okay. 2 parents each has the gene for cystic fibrosis. For each of their children, the probability of developing cystic fibrosis is 1/4. Okay, 1/4. If there are 4 children, find the probability that exactly 2 develop cystic fibrosis. Now, you know what I said about exactly here. In this case, our probability of interest would be focus. What we are interested in is equal to 2. So instead of greater than or less than, you now have equal to 2. That isn't the case. So let's just see the next page, how it is solved, even the one I've just done. So look at the screen again. Can you see how it is solved now for this one is when your question is in phase with what you have there. Let me see. Okay, good. So you can see probability 4/20, and this n combination x, p to the power of s, q to the power of n minus x. And then your probability of interest will be the summation of the individual probability of random variable x. And then you find it independently and you sum everything together to get your answer. Now, for the second question is saying probability of x exactly 2. Okay, so in that case, that means your x will be 2. So you do it for combination 2, then you apply the formula. Of course, you know your p is 1/4, q is 3/4 here, and your n is 4. So that's how to calculate that. Now I'm going to leave binomial. We have spent too much time on binomial. I want us to go into Poisson distribution. Now this is another example of binomial. Let me just explain this. Another example of binomial: 25 individuals are susceptible, each susceptible to tuberculosis, come in contact with carrier of the disease. Probability of the disease will be passed from the carrier to any suspect, any given subject is 0.1. How many are expected to contract the disease? Now, when you ask the question expected is the same as asking for the mean of this distribution. Okay, and to calculate the mean of this distribution, what you simply do, you know, the formula is given as E is equal to NP. Okay, that's how to calculate for expected under binomial distribution. And it's also described as the mean of the distribution. Your N is, of course, your number of possible trial, while your P is your what? Is your probability of success. So, and what is given to you here is the probability of success. This value given to you here, this value, this 0.1 is your probability of success. So all you need to do is to import it into this formula, and say the question says 25 individual. So what you just do is you come here, you say it's equal to n is 25, and our p, which is probability of success, is 0.1, which is the same thing as 1/10. Okay, let's put 0.1 there. If you multiply the two together, should give you the desired answer, okay? Which will be the expected number of people that will contract the disease. Now, you can also calculate for this second question. Somebody is commenting here. Please, what is the technical term for E? The E is expected. Expected. E is expected, okay? So, we also have another question there. You can solve that one on your own. So, what is the probability that in screening of 8 students, what are the chances of 3 or more? What is 3 or more? From what I've explained, what will now be 3 or more? That will be probability of X, our random variable X, that is X greater than 3. That's how to state it, okay? And because you are dealing with 8, okay, it means probability of X greater than 3 will be the sum of, you have probability of S is equal to 3 plus the probability of X is equal to 4 plus probability of X is equal to 5, on and on like that, okay, until you get to 8. Now, let me quickly explain something here. Now, you can see, let's use our whiteboard. Is the question I'm trying to explain here clear? The second question here, is it clear? Anybody? Are you still there?
Sorry, sir. Please, I have a question.
Okay, quickly. Send it in.
What are the chances that 3 or more are colorblind?
Okay.
So I thought it was supposed to be greater or equal to 3, since you said 3 or more.
Yes, is greater than. What's the inequality sign on the screen? It's greater than, of course. Isn't it?
I thought it was supposed to be greater than or equal to 3.
Yes. If you have been following me, I said we don't necessarily say equal to. Okay? The right thing should have been to put greater than or equal to here. Okay? But in statistics, it doesn't count. Do you understand? But it doesn't imply, but it implies greater than or equal to, but we don't necessarily denote it that way. Do you understand what I'm saying? So if you want to leave it like that, just leave it like that. There's no issue with it. There's no adverse consequence putting it like that. But usually, when you say it's greater than, we see it also as equal to 3. Okay? I hope that is clear. Okay, good.
Yes, sir.
Let me activate my whiteboard and illustrate this. There's something I want to bring out here now, and I want you to pay attention very well. I want you to pay attention very well. Okay? So I've said that the probability of interest is X greater than 3. Okay? Which actually should be probability of X is equal to 3 plus probability of X is equal to 4. I'll put dot here until I have plus probability, there should be a P here. Probability of X is equal to 8. Now, if you see this, you agree with me that this is going to be a very long computation. Okay? Now, usually, instead of going this route, okay, instead of going this route, there's a way you can go through the shorter cut. Okay? Recall that probability must always sum up to 1. Okay? So if this is your interest, why not go through the shorter route and just say 1 minus probability of X equal to 0 plus probability of X equal to 1 plus probability of X equal to 2. Okay, so in other words, we can just, instead of finding this probability of the first one I stated up here, x is equal to 3 to 4 to 8, why not just subtract the one of probability x is equal to 0, x is equal to 1 and 2 from 1? Whatever is left will be the rest. Do you understand that? Hello? Do you understand that?
Yes, sir, from my own side.
From your own side. Okay, which other sides?
Yes, sir.
Does it make sense to you what I've just done? Or what I'm trying to explain? Does it make sense to you? Hmm?
Yes.
Sir,
Ivan, right? Good. Go ahead. What do you have to say?
sir, I do not understand this last process now that we arrived at. Why did we shifted it to x equal to 8? Why did we stop there?
No, because it is probability of x greater than or equal to 3. Everything greater than or equal to 3. What is the question itself? Recall that the question gave us, let's go back to the question. We'll come back here. Let's go back to the question. I hope you're following. See the question here. It says, what is the probability that in screening 8 students? Okay? In screening, 3 out of, not the chance that 3 or more are colorblind. Out of 8. Okay? 8 is the maximum number. When you say 3, it means 3 or more. It means it could be 3, it could be 4, it could be 5, it could be 6, it could be 7. But it can't exceed 8 because you are screening just 8. Ivan, is that all right?
Yes, sir.
Okay. So, let's remove my whiteboard. Okay. So, I hope that is clear. That's what I was trying to illustrate. So, what I will now do is I'll close the whiteboard and then we'll finish up on this. So, we've discussed binomial now. So, let me see. Is there any other question there? Okay, good. This is now the calculation. This is just what I just explained. And this is for the second one. Okay? And this is the illustration I just gave. Okay? I hope you are all following me. So 1 minus this will give us what we actually need. Okay? So the next is Poisson process. Recall we have discussed binomial distribution. The next we are going to be talking about is Poisson distribution. Poisson distribution is similar to binomial distribution in the sense that there are 2 possible outcomes too, okay? And usually Poisson has to do with large events. An event that has a large trial size, but the event is rare. The event is rare. Something that is very rare to see. That is what Poisson focuses on. But the same way, you are going to talk about success, you're going to talk about failure, okay? You can have Poisson distribution is model, okay? I've just said this. Now, this is the formula for Poisson. It's different from binomial distribution. Okay? For Poisson distribution, you have exponential to the power of lambda, lambda to the power of x over x factorial. That's the mathematical expression for Poisson distribution. Okay? Well, again, like I said, it deals with a very large event, but rare occurrence. You understand what I mean by that? You see, you said some events are rather rare. They don't happen that often. For instance, car accidents are exception rather than the rule. So still over a period of time, you can say something about the nature of rare events. So Poisson distribution helps us to extrapolate or calculate rare events. An example is improvement of traffic safety, where government wants to know whether the seatbelt reduce the number of deaths in car accidents. Okay? Yes, Poisson distribution can be useful to answer the question about the benefits of seatbelt use. Okay? There you see some other examples of rare events. The Poisson distribution is actually derived by the French mathematician Simeon Poisson. That was in 1837. His name is Simeon Poisson, and it was first applied to number of deaths by horse kicking in the Peruvian army. That's just a little bit of history. So you have an example here, arrival at bus stop following Poisson distribution. There are times a question is given to you and it will be stated to you, or a hint will be given to you that this follows a particular distribution. It makes life a lot easier for you, okay? But it's important you be able to tell the distribution equation follows even without a hint, and I've explained that. And that you can do having clear understanding of the properties of the individual distributions in statistics. Okay, so you have Poisson distribution with an average of 4.5 every quarter of an hour. Obtain the bar plot of distribution, assume a maximum of 20 arrival in a quarter. Calculate the probability that fewer than 30 arrival in a quarter of an hour. So it also follows using your inequality model, okay? It's important to understand how inequality applies. The same way it applies to binomial, it also applies to Poisson, okay? Now you have probability of 0 up to 2 arrival can be calculated directly from the formula, okay? You can have, you already been given the lambda. The lambda is like the mean of the distribution, or call it the rate of the distribution. When you look at the question, let's flip back to the question again. The 4.5 every quarter of an hour, that is the rate, and that equates the mean of that distribution, and that is your lambda. And you see your lambda here. Exponential to the power of negative lambda, lambda to the power of our random variable, okay? So what you simply do in this case is that the question is asking probability of 0. You just replace this x with 0. Replace x with 0. You know the value of lambda already. This exponential is a constant that will be given to you, okay? This exponential is a constant that will always be given to you in your calculation. Okay, so you can see probability of 0 now is being calculated here. And you got this. Because that the question is asking probability of 0 up to 2 arrival. Okay, so it's going to be a sum of individual probability. The one for 0 has been calculated here, and they got 0.01111. Now the next is to calculate probability for 1. They got this. Probability for 2, they got this. So the probability of fewer than 3 arrival. Fewer than 3. It means less than 3, okay? So that's why we zero it down to 0, 1, and 2. So, and that's what you now add together to get this. It's similar to what you did in binomial distribution. Okay? It's only that the properties are different from binomial distribution. Is that clear? Hello? Do I still have my class?
Yes, sir.
Okay, great. So these are the properties of Poisson distribution. Useful for rare events. Prior size is large. Occurrence of events, space-time. Probability of occurrence very low. And then probability of expected in short interval approaches 0. Okay. So these are just a repeat. Now this is the E, which is the constant I told you. This exponential is 2.7183. It will always be given to you. Okay. So, and this is an example of Poisson distribution. This is another example. We're not going to solve that. The questions are already solved here for you. Okay, so we are going to have a brief introduction to the next type of probability distribution. Recall again that I said there are two categories of probability distribution. We have the discrete probability distribution, and we also have the continuous probability distribution. Now, we are entering into the realm of the continuous probability distribution. And one common example we're going to spend a lot of time on is the normal distribution. I call it normal distribution, or it is usually referred to as normal distribution. Let me write it on the screen so that you will not miss what I'm trying to say. I say normal distribution. Normal distribution. So again, let's get this right. We say probability distribution, you can have it in two categories, okay? You can have the discrete, you can also have the continuous, okay? Example of the discrete, you have the binomial, and also you have the Poisson, okay? Now, example of the continuous is the normal distribution, which we are going to spend a lot of time trying to explain. Is it clear to this level for everyone? Is it clear to this level? Good. So we're just going to look at the properties of normal distribution. Again, and
So I have a question.
yes, question. Go ahead.
So you said your examples of discrete probability in
Hello?
geometric and hypergeometric fall under. Can you hear me, sir?
Yeah, go ahead.
You said that there are two types of distribution where you have discrete and two
Continuous.
categories. So where you have discrete and continuous distribution, probability distributions, and you said binomial and point sum. You said binomial and point sum are under the discrete probability categories.
Yeah, as you have it on the screen.
Okay, so what of geometric and hypergeometric? Because you mentioned those at the beginning of the class.
Yes, there are 4 examples of discrete probability distribution. 4 examples I gave you. But I said we're going to narrow down our discussion to binomial and Poisson.
Just two.
Yes, we're not going to discuss geometric and hypergeometric.
All right, thank you, sir.
You're welcome. So, let me run back where I stopped. Okay, so we're looking at some of the properties of normal distribution, which is an example of continuous probability distribution. Okay. Now, we calculate skewness for normal distribution. You have the formula on the screen. And again, we talk about skewness in normal distribution. Recall I explained this at some point. When I talk about skewness, what does it mean for a distribution to be skewed. Let's activate the whiteboard again so that I can illustrate this better. Okay, so we've got normal distribution, normal. Okay. Okay. Now, normal distribution, let me explain it to you in a layman term. You see, generally in biological science, most data that we collect follows this pattern of distribution. Like I've always used your class age as an example. That if I decide to gather your class age as a data set and I plotted it on a graph, I'm going to form this type of curve. Okay? If I plot it in the graph, I'm going to form this type of curve. When you complete this graph, you have your y-axis, you have your x-axis. Okay? So when I plot it on this curve, this tall portion will be the mean of the class. So this is where the majority of the class member will fall. And the mean will be the mean age of your age, of the data set I got. Most likely, I would personally think that the average age in your class should be around 25. Do you agree with me? Ivan, what's your age? Ivan.
Sir.
What's your age?
Sir.
What's your age?
22,
How old
sir.
are you? You are 22.
22, sir. Yes, sir.
Okay. Harrison, what's your age? Is it there? Harrison. How old are you?
26.
You are 26.
Yes, sir.
Chiamaka, how old are you? Chiamaka, is she still there? Some of you connect. Okay, Chiamaka does not like talking. Okay, 27. You're welcome. Who else am I seeing there? Lillian. Lillian, how old are you? Lillian, how old are you? Where is she? She doesn't like talking to me. Okay, probably she's not connected. Who else there? Who else can give us the age? Ada? Ada, is it? How old are you? Who is using Zaza phone? iPhone? I just want to have a rough idea. Probably we could use that to joke.
Sir.
Yes. Who is
Mine
talking?
is Joshua. I'm with Ivan here.
Okay.
Mine is 22, sir.
22.
Yes, sir.
Okay. Who else there? Any other person? I'm thinking of getting 5 so that we find the average. Ada is not speaking. Okay, so the point I'm trying to make is that, well, over the years, we have taught
24, sir.
24. 24, okay. So, over the years, I've discovered that I've observed that the average age of students in 5th year is usually 25. Okay. So when you plot the graph, and you don't really have people with extreme age in that class, we say the curve that will be obtained is normally distributed, that your ages are normally distributed. So when you say normally distributed, It does not necessarily mean the opposite of it is abnormal, not necessarily. It simply means that the data set follows a typical pattern. It follows a typical pattern that is expected to see, okay, in ideal situation. So we call it normal distribution. Typical, classical, expected, okay? That's what that actually means, okay? So, but in a situation whereby you have people with unusual ages, let's assume somebody is 38 in this your class, okay? It's going to affect the shape of this particular curve. Because that person that is 38 is going to drag the mean to the right-hand side. Somebody can as well be, say, 18 in that your class, and that will also affect the shape. So we refer to these values that are unusual, these strange values, we refer to them as outliers. 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 Okay? Sometimes we call them extreme values. Extreme values. Okay? And what do they do to our curve? They make our curve to be skewed. 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 In other words, they drag the curve. They make it to be they make the curve to be lopsided, bent to one area. Okay? And this skewedness can be in two forms. It can be positively skewed, it can be negatively skewed. Are you following me? Am I making sense? Hello?
I'm not making any
Yes,
sense.
from my end.
Somebody said, I'm not making any sense. Hello?
I said, yes, sir, from my end.
No, somebody said, I'm not making any sense.
Huh?
I'm interested so that I can explain to that person. I want the person to get it. Who is the person? Who just spoke now? It was a female voice I got. No, please speak up. I'm not indicting you in any way. I just want I want to be sure you are following me and also help you out where you are missing it. Please speak up. Be bold to talk. Who said that? Hello? Hello? Ukamaka? Ukamaka, I guess you're the one. She has disappeared. Okay. No, I just wanted to explain to you. There's no hard feeling about that. Okay. So, like I said, these extreme values, these outliers, they affect our curve, making the curve either to be positively skewed or negatively skewed. Okay? And when you have negatively skewed curve, okay, it has implication on our measure of central tendency. I taught you measure of central tendency. And that's the point we started discussing about this normal curve. Okay? So, but there's one more thing I need to quickly explain about this curve before I round up tonight. Our time is fast spent. Now, when you have your curve, your normal distribution curve, like this, and you have your mean at the middle. This normal distribution, okay, it has two very unique properties. And these properties are the mean and the standard deviation. The normal distribution is completely defined by its mean and its standard deviation. Completely defined by the mean and the standard deviation. That is the normal distribution curve. This curve, I call it the normal distribution curve. It is otherwise referred to as the Gaussian curve, after the name of the man that discovered it. Gaussian curve. Okay? It is the dumbbell shape. It has a dumbbell shape. You know how a dumbbell looks like. Okay? So we say the curve is completely defined by its mean and a standard deviation. What does that mean? You know, you can find the standard deviation. You know, in your basic mathematics, you know how to calculate standard deviation. Okay? You calculate variance, you calculate standard deviation. So you can say from the mean to the right, to the left, one standard deviation. Okay? One standard deviation. This is one standard deviation. Can have two standard deviation. Okay? Two standard deviation. Two standard deviation. Now, this is the right side of the curve. I don't want you to miss that. This is the right side of the curve. Otherwise referred to as the positive side of the curve. The positive side of the curve, I believe you have a note you are writing down. And this is the left side of the curve. Okay? Otherwise referred to as the negative side of the curve. Okay? So when you say something is right skewed, okay, it is the same as saying positively skewed. You can say something is left skewed. It's the same as saying negatively skewed. The word skewed, bent. Okay? Is it clear? Is it clear? Am I still making any sense?
Yes, sir.
Okay. Ukamaka, I get your point. So, this looks like enough for tonight. Before we start having, we start getting confused. Any question? Any question?
Hello, sir.
Yes, please go ahead.
Yeah, please, in that Poisson's distribution, you mentioned lambda. What does that represent? I've forgotten.
The lambda is the mean of the distribution.
Okay.
The mean
Okay.
of the
All
distribution.
right, thank you.
Any other person? Any
Sir?
question?
Yes, sir.
Yes, go ahead.
Yes, sir. This is Shamaka. I would like for you to clarify on this expected to, that's the E of X is equal to MP. That falls under binomial distribution, right?
Yes, both binomial and Poisson. Okay? Both binomial and Poisson.
Oh,
The mean of their distribution
okay.
is also described as their expected. And that is E.
The mean of their distribution.
Yes, they have a mean.
Okay.
In fact, you
Okay,
also
so
calculate the variance of the distribution. Go ahead.
the variance of the distribution. I don't remember a formula for that, sir.
We did. Look at it. Look at your screen.
Oh,
Look at your screen.
I'm looking at my screen, sir.
Yes. Can you see the variance now? For binomial distribution. So it is the M multiplied by the P multiplied by the Q. That's the variance. You also calculate the coefficient of skewness. And that's the formula. I've already sent this PowerPoint to you. How many of you have it? You should all have this PowerPoint. I think it was
We should.
I think it was Ngozi that asked for it. And I forwarded everything to her. Even all the PowerPoint I've used for teaching you so far. I forwarded everything to her and I said she should share it. Ngozi, is she there? Has she posted it on the class group? No, that's serious. And she acknowledged them.
We'll remind her, sir. She probably did not remember. So I have my second question, sir.
How can she forget such thing? I sent all the PowerPoint to her and I emphasize, I wrote it in capital letter. Please share this with the class so that I don't have to spend more data sending it to everybody. I shared about 5 documents with her.
Sir.
So she has sent it.
She has sent it.
Some PowerPoint were sent.
Okay. That's what I need to hear.
So she has sent it.
Okay, good. Any other thing again?
Yes, can you elaborate more on this measure of central tendency? You mentioned it when talking about normal distribution and the top of the curve.
Measure of central tendency is a topic on its own. Were you in that class? Were you in that class when we discussed measure? So that's it. Everything is interrelated. Are you getting it?
Okay.
They are all interrelated. When I say measure of central tendency, I just talked about the age. Let's assume I collected your class ages, the various ages, individual of your class. Can I calculate the mean? Of course, yes. Can I calculate the median? Yes, I can calculate the mode. These are measure of central tendencies. So maybe it's the terminology you are not familiar with. I don't want to believe you are new to that main median mode.
All right, thank you, sir.
You're welcome. Any other question? So let's round up with the property of normal distribution, which I started explaining the other time. I said this is called the Gaussian curve, as you can see it on the screen. Okay, it is described as the Gaussian curve, the normal distribution curve, and it occupies central role in statistical inference. This normal distribution, if you don't know it, you can never know statistics. If you understand this normal distribution, you will understand more than 50% of statistics because it occupies a central role in statistical inference. Very, very important. Very, very important. Okay? Please pay attention. They are not difficult. It's just you putting your mind to them. So the property, bell shape, symmetric about the central value, completely determined by the mean. This is what I said the other time, that the normal distribution or the normal curve is completely defined by the mean and the standard deviation. Mean and median mode have the same value for a normal distribution. Let me repeat that again. The mean, the median, and the mode, they have the same value for normal distribution. The total area under the curve is equal to 100 degrees. 68% of all observation lies within one standard deviation of the mean value. 95% of the observation lies within 1.96 standard deviation of the mean value. And 99.7% of all the observation lies within 2.58 standard deviation. These are the properties of normal distribution. We're going to pick each of these properties one by one and express what's one by one and explain what it means. Okay, just come along. Okay, now we can express normal distribution mathematical in terms of graph. I show you the graph, that's the dumbbell shape, and we can have it in form of table. Okay, so we're going to discuss the use of table in solving normal distribution. We're going to discuss how to use mathematical equation and how to use graph. Okay, now I will revisit my assignment again now. I told you to prepare the names of all the class members, as many that are ready to participate. Prepare the names, the various ages. Everybody must disclose his or her age and put it on that table. The height, you put it in table. Put the weight. Go and measure your weight. Know your weight, your height, and put it on that table. Are you getting my point? Okay. And now from that data set, you are going to calculate the standard deviation for me. You are going to calculate the variance, the class variance, the standard deviation. Are you writing this down? That's my assignment for tonight. Okay. You're going to calculate standard deviation, you calculate the variance. If you don't know how to calculate standard deviation, go online. Check the internet. Check how to calculate variance. It's part of the work, elementary mathematics. So we're going to, you are not going to plot a graph. You get a graph book and plot the ages on the graph. You plot the age, the class age on the graph. I want to see how the graph looks like. Okay, of your class. And we'll begin to discuss the symmetry and the rest of the thing. Now, we're also going to be using table. For all this distribution I'm telling you about, they have what we call table. Just like you have four-figure table. How many of you are familiar with four-figure table? I know some may have forgotten. That you go and look up value in four-figure table. We're going to be looking at value, looking up value on table. We have Z-score table. We have different type of table we are going to be looking at. Okay? Just get yourself ready. Now, this is the mathematical equation for our, what's it called now? Our normal distribution. This is the formula. Just like I've shown you the formula for binomial distribution. I've shown you the formula for Poisson distribution. This is the formula for normal distribution. Okay? This is the formula for normal distribution. And you can see here we indicate the mean and the standard deviation, because the normal distribution is completely defined by its mean and its standard deviation. Anyway, don't get your heart yourself worked up. We're not going to be applying this formula. Rather, we're going to be doing our calculation in a different way. Okay? So this is the normal distribution curve that I just drew for you the other time. Okay? Now, if you look at this curve now, this is described as the point of inflection. This point, let me get it right. Okay? This is described as point of inflection. Inflection of the curve. Excuse me, please. Point of inflection. Inflection. Okay? Now, usually for normal distribution, this particular portion does not touch it doesn't touch this line. It just tail off like this. It doesn't touch. Okay? This is the peak of the curve. You see the peak of the curve, this top portion. And this is where your mean will usually start at the middle. Okay? So some of the formation you need to get familiar with. Okay, battery is 1%. Don't worry. We are rounding up. So this is still the curve again. And these are some of what I described. Now, there is what we call total area under the curve. The total area under the curve is described as 1 or sometimes 100%. You see, probability of any single value is given as 0. Okay. Table of area, we're going to look at that in detail. Now, there's what you call, okay, no. Let's not go into this night so that we don't mumble things together. So we're going to start from that in the next class. We're going to be looking at transformation of a normal curve. How do we transform a normal curve? Okay, this will be it for tonight. If there's any question, please, this is the time to speak up. Any question, please? If there's any question, please, this is the time to speak up now. before I end the class. Any question, please? Hello, Doc. Good evening. Are you there?
Good evening.
Good evening. Sorry, we kept you awake too.
I'm watching the class. I hope they are getting it.
I hope so too. At least
And I
today.
want to believe that the 16 we have is not the 16 for the whole class. Worried.
I would have thought a virtual class like this should be more relaxed for them.
Yeah.
Because the implications are they going to just go home and forget about everything? And you won't have much time. But by the time the years starts, there won't be much time again because it's counting. The days are counting.
Exactly. Oh, please, the class should encourage those who are not always coming online. So please come. So that we don't have problems when it's obvious that if it's just, I want to believe the 16 we have here is, let me believe
It's even 15 now. Okay, it's even 14.
let
If
me
you
say we have
it's 14. If you remove yourself, it should be 14.
So you see, out of 50 something, how many are there in the class?
In fact, I counted myself. There should be 13. Sir. They said there are 92 in the class.
And we're having 16, 14.
And in fact, I learned
sometimes
that
you won't blame.
I learned the class, the receipt exam has ended now. They are only left with practical.
Receipt exam is ending next week, sir.
So I won't blame them. What's the reason for it? Do you have a reason for it?
There is power outage in some parts of the school. Like, I'm very sure that a lot of girls are not here night at my side. That's the I'm staying. Then secondly, network.
Network.
Yes, ma'am. Because I know in previous classes how many times network has kicked me out of the class and I will still try to join. I'll still try to rejoin.
It's the same MTN we are using. I'm using
No, I'm not
MTN
using
yet.
MTN, sir.
Okay.
But then please, you should switch to MTN now. If you know that's disturbing you, then you look for a better alternative. How about Lionel? Is it not working? I see people cluster around